keep enhance them in higher dimensions.
Thank you very much. So many thanks to the organizers for giving me the opportunity to speak. It's a great pleasure. And this is joint work with Rainer and with Stefan Weiss. So let me start with setting up what Kippenhahn's theorem is all about. And it's about the numerical range of a complex matrix. So and I don't know, it's something that, but I'm sure that many people are familiar with, probably know much more about than me. On the other hand, maybe some people haven't seen the definition at all. It's the simplest thing. So you have a complex D by D matrix. And the numerical range is simply the set of all values that you get from A by treating it like a Hermitian form. So you do x star AX. And this gives you, you run over all vectors of length 1. This gives you a subset of the complex plane. And that's the numerical range of this matrix. Okay. And so what kind of information does it contain? So first of all, there's a somewhat miraculous fact that this set is convex. So, so this is the Triplets-Hausdorff theorem, which tells you that this is a convex set. There are a number of different proofs for this. It's often proved in functional analysis for bounded operators in a Hilbert space, not just for matrices. There's a very nice proof in Babinok's textbook on convexity that sort of puts it into a more general framework of what he calls quadratic convexity. But no matter how you prove it, it's not obvious. It's not something where like convexity often is, you just apply the definition, you do a convex combination, you see it. No, I mean, it's a somewhat non-trivial fact that this is a convex subset of the plane. And more generally, so what can you say about it? So first of all, I mean, of course, if you have a Hermitian matrix, then this takes only real values. So then you get a real line segment. But this is if and only if. So I mean, a Hermitian matrix has real eigenvalues, but I mean, just because a matrix has real eigenvalues doesn't mean it's Hermitian, right? So this is one way in which the numerical range already contains more information than just the eigenvalues, right? It is not invariant under similarity of matrices. It's not invariant under base change, so unlike the eigenvalues. So it captures, in this sense, more information about the matrix itself. So more generally, if A is a normal matrix, so if it commutes with the adjoint, then it's just a convex hull of the eigenvalues. So then it's a polytope. But in general, okay, it's just a convex subset of the complex plane. So the example that I'm going to use for the next couple of slides will be this lovely little 4x4 matrix where you just shift and scale with 1, 2, 3, and 4. I already see Cynthia smiling. She likes this. I know you like this matrix. So for this matrix, so this is not a normal matrix. And so, okay, so the numerical range is a subset of the complex plane. It looks like this. Okay. I mean, it's not a very exciting picture. I mean, after all, it's a convex subset of the plane. So, I mean, how much excitement can you expect? But nevertheless, so we will see that it's even for this very simple example, actually the exact geometry of this subset of the plane is not as trivial as the picture suggests. So, all right. So there's a hyperbolic curve associated with this, and that's the subject of this Kippenhahn theorem. So what you do is you take your complex matrix and you split it into real and imaginary part. And not coordinate-wise, but in this, so you take the matrix real and imaginary part, which works like this. You do, okay, A plus A star half and A minus A star divided by 2i. And this, so this makes it two Hermitian matrices, right? And of course, so as it should be, A is real part of A times I times imaginary part. And for example, so in this running example, if you do this, so even though it's a little, I mean, for me at least, it's a little bit confusing, right? I mean, you start with a real matrix, But the real part, of course, it's not that the imaginary part is 0, right? I mean, in this case, the real part and imaginary part, so they turn out like this. Okay, these are two Hermitian matrices now that add up to A. And so what you can do now is, so these are two Hermitian matrices now. So if I take this determinant, so you do x0 times the identity plus x1 times the real part plus x2 times the imaginary part, then because I have two Hermitian matrices and put the identity here, this is a hyperbolic polynomial. Okay, so it's hyperbolic with respect to 1, 0, 0. So which in this particular case with these coordinates just means that if you fix the last two coordinates and let the first one run, then you have a real rooted polynomial. And so this will be, so and in fact, I mean, by the Helton-Winikoff, so first of all, of course, any determinantal polynomial in 3 variables can be, you can write it in this way, and then by Helton-Winikoff, this is really all hyperbolic polynomials in 3 variables, more or less. And so then there's this familiar picture of the curve geometry. So we look at this in the, so I mean, this is supposed to be a projective picture, but really you can just assume that x0 is equal to 1. Okay. So which leads to this kind of picture. It's a slice of the 3-dimensional cone where you put x0 equal to 1, and hyperbolicity means that the hyperbolicity cone is this, the slice of the hyperbolicity cone is this convex region here in the middle, and geometrically hyperbolicity means that if you take any line that passes through the hyperbolicity region, you see only real intersection points, right? Which is, I mean, I'm sure everyone has seen this probably at this point. I mean, it's a little bit different from the usual definition of hyperbolicity, but that's what it comes out to if you draw these kind of plane slices. So this is an example of degree 6, and was not the running example that we saw. But I'll get to that example now. So what is the statement of Kippenhahn's theorem? So you do this, you start with your complex matrix, you split it into real and imaginary part, you get a spectrohedron defined by these two Hermitian matrices. And so what Kippenhahn's theorem, what it says, so from 1951, it may be one of the oldest theorem involving hyperbolic polynomials in a way. Well, it says that the numerical range that we looked at before in the complex plane, if you identify it with R2, then the numerical range is the convex dual of this spectrohedron. And moreover, it's given, it's more precisely, it's the convex hull of the dual curve of the plane curve defined by this polynomial. So the statement, the way I phrased it, the statement has two parts. One is just this duality statement, and this in fact is just general convexity. I mean, here in this setup, it's written down in a slightly confusing way, so it's maybe not obvious. In the later when we look at the more general part, it will maybe be more obvious. But just trust me that so the fact that this is that the numerical range is the convex dual of this thing is just general convexity. Whereas the second part of the statement that involves the dual curve, this is the, if you want, the hard part of the theorem. So what is this? What is the dual curve? It's the dual curve in the sense of projective geometry, not in the sense of convex geometry. So it just means it's the curve that parameterizes all tangent lines to the curve, right? So you have dual coordinates. So you have primal coordinates x0, x1, x2. You have dual coordinates u0, u1, u2, and you look at lines with these coordinates, and you pick up all tangents to the given curve. This gives you a new curve in the dual plane. That's the dual curve. And so let's do this. Sorry. So yeah, so we will get to that in a moment. That's exactly, that's what it's all about in the end, right? So what does it exactly have to do with the convex dual? It's not so clear. So let's do it in this. Okay, so are there any questions up to here?
So is the numerical range compact?
Yes. I mean, you started with the vectors of length 1, right?
Therefore, this dual curve is compact.
Yes.
Or that's part of the statement. The dual curve.
Yes, that's part of the statement. The real part is compact. Yes. Okay, let's look at the example that I had in mind. So let's do this lovely shift matrix. So if you do this, you take the determinant, you get this this for the boundary of the spectrohedron. This is this curve of degree 4, and this is the picture here. And it has this nice symmetry which comes from the shift structure. So that's the primal curve, and now you take the dual curve, and the dual curve, so this is a quartic, the dual curve will have degree 12. We'll get to the general statement in a moment, and it's a degree 12 curve in these u coordinates, and this is the equation which you can compute by elimination. And this is the picture that you see. Okay. And so why does it look like this, right? So what is the meaning of the picture? So first of all,
the numerical edge is this big oval.
Exactly. So this was the picture that I showed you at first, where the inside was not visible. So by Kippenhahn's theorem, the numerical range is the convex hull of the dual curve. And that was the first picture we had. It's just the convex hull of this thing. So it's even somewhat stronger. I mean, the dual curve, the dual polynomial vanishes on the whole boundary of the numerical range. So this is what you see, and so this stuff in here that contains the more interesting geometry, if you want. So the outer oval comes from the little convex region that we really care about, and this takes care of the rest. And it's singular, which is what always happens. The dual curve of unless for conics, the dual curve of a smooth plane curve has singularities, and the singularities have a meaning. So you get nodes where the curve crosses through itself for bitangent lines of the original curve. So here you have a line that's tangent twice to the original curve, and if you think about it, as the tangents move along the curve, this will mean that the dual passes through itself. Geometrically, it's kind of suggested. So you get nodes that come from the bitangent lines. And you also get cusps, like here, and the cusps come from the inflection points of the primal. This is where the cusps arise when you go through. So this is 8 cusps, and they come from the 8 inflection points that sit in between. Okay, so that's the geometry.
This is Klucker's formula.
Exactly. So this I'll have that on the. You're very good at predicting what I'm going to say next. So this is exactly. So this will be on the next slide. So that's to say this again in general. So if you start with a smooth curve in the plane, then the dual will be irreducible. It will not be smooth, but it will be irreducible of degree d times d minus 1. And generically, you see 2 types of singularities. You see the nodes coming from the bitangents, and you see the cusps coming from the inflection lines. And indeed, so classically, there are the Plücker formulas, very classical geometry that count these singularities. So for a generic curve, if you do the count over the complex numbers, these are the formulas. So you get 1/2 d times d minus 2 times d minus 3 times d plus 3 nodes corresponding to bitangents, and you get 3d times d minus 2. So, but this is, of course, it's a complex count, of course. So this is for the complex curve. And so in a second, it will become somewhat relevant what happens over the reals, not with the count, but nevertheless. So, if you want to do this count over the reals, so what is known, what is also very classical, is that you can have at most a third of the inflection points can be real. But how many bitangents are real is somewhat, in general, or can be real is somewhat harder to say in general. It's known in low degrees, but I don't think there are even exact. I don't think this is even exactly known in higher degrees. But typically, you can have all of the bitangents real, or or maybe very few of them. Okay. So I really want, so this is the plain statement again of Kippenhahn's theorem. And so I want to treat this plain case carefully and explain the idea of the proof. So why should this be true? So if you look at it sort of proof by picture, it actually is, the whole thing actually is very simple. So you want to say that the convex dual of this thing in the middle, which is the spectrohedron that we wanted, you want to say that that will just be the convex hull of the dual curve. Okay. So why is that? Well, so this means basically that this will dualize to some convex oval again. That's clear, and you want to say that everything else will be inside this convex thing. And why is that true? It's true because if you have tangents somewhere to the curve somewhere else, then so what does it mean in the dual to be outside of this oval? Well, the points outside correspond to lines that pass through the central region. And if you're hyperbolic, a tangent somewhere outside cannot pass through the interior here. So this is, the picture suggests it, and it's a general fact about hyperbolic polynomials, which is extremely useful, that for lines through the hyperbolicity region, not only are all the intersection points real, but you actually cannot become tangent anywhere. Okay, this is, you can write this down with derivatives, of course, but geometrically that's what it means. Okay, you cannot become tangent anywhere else. And that's the reason why, since you can't become tangent for any lines through here, that's the reason why everything else stays inside. And that's why the theorem is true. However, so if you really want to make this into a proof, there's a nagging detail, which is that, so this is all good and well for the things that actually come from smooth real points. Okay, but remember that the definition was a complex construction. So in particular, what you wouldn't see in the picture, so what happens, so the worrying thing is what happens, you could have some nodes, some real nodes that are isolated singularities of the dual. And you wouldn't, okay, and so what happens to those? Why can they not show up? So for example, so I can certainly do an example where you do get such isolated nodes. So here's another example which looks at first even more boring. So this is another quartic where you really just have two convex ovals, okay? So absolutely nothing happens this was the prior picture, this was the dual picture. Okay, the picture looks exactly the same. This is again the equation. This is a degree 12 curve. It's not hyperbolic, of course, but it still just has two ovals. But actually, if you look more closely, it so happens this thing there has four real bitangents that don't look like bitangents. So these are four real lines, but they're tangent to two pairs of complex conjugate points. Right? Bitangents. They are tangent at two pairs of complex conjugate points. That's also a valid bitangent according to the algebraic definition, unfortunately. And it leads to nodes on the dual curve. And these nodes, Mathematica didn't plot them because they are isolated points, but you can find them. These nodes are isolated real points, therefore isolated singularities of this dual curve. But again, they do all gather nicely in the inside of the outer oval for much the same geometric reason as before. If you are a line that passes through the hyperbolicity region, you can't be tangent at real points. You can even less be tangent at complex points, right? Because all intersection points are real. So definitely these singularities they will not show up inside the convex hull. But the only reason I emphasize this so much is that this subtlety, this interplay between the complex and the real curve, this is exactly what will make life much harder if you go away from curves. So for curves, it's all good. And so I hope you all agree with this. So I mean, I've now told you all the ingredients that are needed to turn the pictures into an actual proof. Okay, this is the reason why.
So to understand the picture, so it could happen that these red dots also travel to the inner oval on the right. So if there is a...
Yes. That's true. That's true.
They're always there. They're always the 4 red points, but they can be either inside or they can sort of move and touch the right inner oval.
Yes, this is just, so this would just mean, right. So
They cannot escape, but they can go...
they cannot escape, but they could. I mean, it would just mean that these bitangents, so it can't happen in degree 4, right? But it would mean that these bitangents somehow cut through the curve, not through the inner oval, but cut through the curve somewhere. And of course, in higher degree, that could happen. I mean, it's here is degree 4, so they really have to stay outside, but it can happen in degree 4. But in higher degrees, yes, it can happen. They can travel somewhat to the outside, but they can't really escape the outer oval.
But sorry, I'm missing the point. So why should I worry about those? I mean, somehow if in there I'm concerned about the inner...
Well, I was just arguing that everything in the... I was arguing that everything is in the inside, right? But where does everything come from? So everything means all the real points, okay? But the real points can...
connected components, right?
Yeah, I mean, the real points in the dual, where do they come from? They come from real lines, but the real lines don't have to be tangent to real points. So the argument that I was making before, okay, where you look at the outer ovals and you move the lines around a bit, this was not completely rigorous for this reason, right? There are also real lines that are tangent, but they're not tangent in real points. So then, okay, you need this refined, for this situation, you need this refined argument. That's the reason, okay?
So if one of the dots were outside and you take the convex half, you get too much. Then you get a polyhedral bit that you don't want.
So I can certainly produce, well, I should have done that actually. You could certainly produce a picture of something that's not hyperbolic, okay, but still you get a nice convex inner oval and all the, just looking at the real points, the geometry works out nicely, but then in the dual you would get such an isolated point outside and the convex hull would be wrong. You could definitely, I should have made up such an example perhaps, but this could definitely happen, okay? And the reason, we say this again, the reason is that, so the real points of the dual curve, they correspond to real lines, actual real lines, that are tangent to the curve, but the points of tangency do not have to be real points. So that's the thing that's tricky between the real and the complex geometry, right? Is that the tangency is there, but you may not see it in the real picture.
Okay. So, sorry, question. Yes. So the statement holds for homogeneous polynomials, right? You just stated it like that, right?
Yes. So, yeah. So I made everything homogeneous, right? So if you look at the equations I'm giving, all the curves are homogeneous. Yeah, all the equations. So by definition, all the curves are homogeneous, which is a little contrary to this setup. Actually, you want x0 to be equal to 1. I'm sort of going to sweep this under the rug. But you have to do this going back and forth between the cones of the projective variety and these slices that we care about. But this is, I mean, if you do it carefully, just believe me that all the statements will be compatible. There's no problem with taking these steps. But you have to, I mean, all the curve theoretic statements and so on that are made are for projective curves, and they're not really true if you only do alpha.
So one of the colors, it doesn't depend like on how you write down determinant representation. The numerical range is always the same, right? Like you can represent a different.
Sure, it only depends on the curve. So you could look at different determinant representations of the same curve coming from your original matrix. And I think people have actually looked at this, Chen and Makazato. It's not so clear how this, I mean, how are these new matrices that represent the same curve, how are they related to the original matrix that you wanted the numerical range of? I mean, not in any obvious way, except that they have the same numerical range.
It's not obvious that they should have numerical range the same, like without this theorem.
No.
Okay.
No, it's only obvious because if you know that they give the same curve. I mean,
Are these, what happens if you take unitary, conjugate the matrix by unitary? So the numerical range doesn't change?
Yeah. And this is
And,
what,
oh, this doesn't, okay, this doesn't.
or you do it to
Oh,
the
it's just,
whole
yeah,
matrix.
it's just,
Exactly.
So all of these invariance things, this you can see from this representation. It's probably also possible to see it directly. But yes. Again, it's a little tricky because you're doing transformations on this real and imaginary part, right? Not on the original. Okay. So this is what I was going to say about the case of plane curves. And in higher dimensions, I really want to get only to one punchline result. So before I go on, so are we all happy with the original Kippenhahn theorem and the plane case? Okay, so now we go to higher dimensions. And this means we'll look at the joint numerical range of several matrices. And in fact, in this case, we are going to assume that the matrices are already Hermitian that we start with. Okay, this is a difference. So we take Hermitian matrices, but more than one. Hermitian matrices A1 to AN. And then we can look at the same thing as before, but for all the matrices together. So we just do x star A1x to x star ANX for x of length 1, and we get something in C to the n. I'm sorry, we get something emission matrices. We get something in R to the n. This is a typo. So now this is the point. This is what I was saying. We take our emission matrices. So of course now we are in R to the n. Sorry. And so in this case, so what happens? So first of all, so what does this thing mean? So this joint numerical range, it's a little bit less, so from the original motivation, say, it's a little less what information exactly it encodes about these, about the matrices. It's been studied in matrix analysis. Our co-author, Stefan Weiss, so he comes from mathematical physics, and this seems to be where most of the interest currently comes from. So people look at this in quantum physics as a statistical model for the state space of a quantum system. But I'm really just saying words. So I shouldn't advertise this, but just saying words that I hardly understand. So I'll stay away from the quantum physics. But this is where some of the motivation and recent studies of this thing comes from. So sadly, if you the first thing that you notice is if you do this, the triplets Hausdorff theorem does not transfer, so this thing will not be convex in general. So this has been looked at in some detail. So sometimes it still is convex. You can produce special cases where it stays, very special cases where it does stay convex, but in general, this will just not be the case. You do not get a convex set. So nevertheless, we can just take the convex hull, and it's easy to describe it in the same terms. So here I'm just taking vectors of length 1. I can rewrite this in terms of a trace, right? So if I rewrite this with the trace, then this becomes A1 x star. And x star is a rank 1 positive semi-definite matrix of trace 1. So if you start taking convex hulls of these things, you will just end up with this. So you take the scalar product A1 with x, where x is any Hermitian PSD matrix of trace 1. Okay, so that's what the convex hull will be. And this thing, of course, so this is something that we feel very familiar with. So this is just a linear projection of the cone of PSD matrices. Okay, Hermitian matrices, but nevertheless PSD matrices. This is a spectrohedral shadow. And more specifically, it's actually just the dual. Again, this is dual just to the spectrohedron. And in this sense, it's the same as before. This is the dual. This is the convex dual of just the spectrohedral. The spectrohedron. I put the identity here, so the identity will give me this trace equal 1 condition when you dualize, and then you just take this spectrohedron defined by these n Hermitian matrices. And the joint numerical range is the convex dual of these. So maybe I should say the convex hull of the joint numerical range. I should say that the terminology seems a little bit in flux at this point. So some people call this convex hull the joint numerical range, and some people call this the joint numerical range, and some call this the spatial numerical range. Okay, I don't really know what to call it, but to be perfectly clear, I will just say it's the convex hull of the joint numerical range. And anyway, this convex hull is just the dual of this of the spectrohedron.
Sorry.
Yes.
Like what the right-hand side is the same. I don't understand.
What do you mean the right-hand side?
The first definition of the joint
It's the
numerical range.
convex hull.
It's the convex hull, right? I take the convex hull because I've now, this is rank 1 matrices. This will be if I put x of rank 1 here.
Okay.
Okay. But I'm taking the convex hull, and then I just get all permission matrices of trace 1.
Like the entries of the vector in the numerical range in the first line, like they are also of this form, right?
Yes, but rank 1 matrices.
If your x is rank 1, what? If your x is rank 1 on the
So I'm just taking a vector here, x and cn.
Right, exactly.
So this is clearly a subset of this, but here I've taken the convex hull because I'm allowing matrices of. Anyway.
Okay.
Okay. All right. So and this is okay. So whatever this is, it's still just a dual of this spectrohedron. And so now the question is, can we still do something like in Kippenhahn's theorem? So I mean, duality for spectrohedra is not so bad. We do this in SDP all the time. You have a dual. If you have an SDP, you have a dual SDP. But that in fact does not mean that you have very good control of the dual cone of the. Even in the spectrohedral case, this does not actually give you an immediate description of the dual cone. So the question is, do we still get this statement from Kippenhahn's theorem? So can we still combine this with the duality of projective varieties and take the convex hull? Okay, and this will be so we try to do the same thing as in the plane. So the general definition of the dual variety now is very much like for curves. You have a projective variety V, and you just take all hyperplanes that are tangent to the variety. So if the variety itself is not of codimension 1, so then its tangent spaces are lower dimensional, but you just take all hyperplanes that contain the tangent space at some regular points. You take all hyperplanes that are tangent to the given variety V in some regular point, right? So the definition says there exists some regular point where the tangent space is contained in this hyperplane defined by this equation, and you collect all these coordinates, you get the dual variety in the dual projective space. And this behaves somewhat similar to the case of plane curves. So here are some facts. So the strongest statement about this, so if V is irreducible, we still get, I didn't actually say this for curves, but you get biduality. So the dual of the dual is the original variety. Anything that doesn't satisfy this shouldn't be called a duality, right? But it's actually not easy to prove. So for curves, there's the somewhat, even for curves, it's a little bit surprising at first because the degree goes up in the dual, as we saw, right? The degree, if you start with a smooth thing, the degree jumps from d to d times d minus 1. And now if you do duality again, the degree suddenly drops. But that's, of course, because the dual curve is not smooth. And the same thing happens here. So you do get biduality. So this is, for instance, it's in the textbook of Gelfand, Karpanov, and Zelevinsky. This is a proof of this general biduality theorem. I actually don't know when this was first proved in full generality. Some special cases, certainly classical, but which is the first reference for a general proof, I don't know. And again, so in the generic case, it kind of behaves like you would expect for curves. So if you start with a hypersurface and it's generic, random, then the dual is again a hypersurface of some higher degree d times d minus 1 to the n minus 1. But in contrast to curves, the situation that we care about with the spectrahedra, so determinantal hypersurfaces are not generic in this sense. So in fact, they're highly non-generic. So determinantal hypersurfaces usually they contain linear subspaces. The hypersurface contains linear subspaces, and this means that you get less degrees of freedom in the tangency, and it means that the dual variety, the dimension collapses. So in fact, the most extreme example of this is if you just take the general determinant. Okay, if you just take the general determinant, so you can think of it as a hypersurface in the space of all symmetric d by d matrices. You take all matrices, symmetric matrices of rank less than d. This is the determinantal hypersurface, and the dual of this is just the set of all symmetric matrices of rank 1. So which is what in algebraic geometry is the Veronese variety. So this has dimension in particular. This has dimension, well, d plus 1 choose 2 minus 1, the determinantal hypersurface, and this has dimension d. Okay, so the dimension collapses completely. And if we go to general spectrahedras, we start slicing this thing, and we will see some version of the same phenomenon of dimension drop. And so without all this, even without all this projective, these general facts about duality, so people studying the joint numerical range, they did look at this. Okay, let me first, all right, I forgot about the slides. It's just too nice not to mention. So it's a famous classical example, just to see some nice variety and dual variety. A famous classical example is this duality between a singular cubic surface in P3, which is Cayley's cubic, defining the elliptope as a spectrohedron, and its dual surface is a quartic surface in this case, so the degree goes up, not by so much because it's a singular surface, but the dual is a quartic surface, and it's this blue thing here. It's the actually this is cut off, but this is a quartic surface which is dual to Cayley's cubic, and you can see it's highly singular. Yes.
Should be higher range also, right? Or
well, if you want the dual convex body, exactly. So what happens is this thing is not convex actually. So if you want the convex, dual of this thing, there will be some part when you take the convex hull of the dual, you will have to have some cutoff. So you have to get the convex dual, you have to put some lids on this thing. Okay, you have to put some hyperplanes. You have to put 4 hyperplanes corresponding to these 4 singular points. They will sit like lids on the projective dual to give the convex dual. Thanks for this question. So this exactly. So it shows exactly the kind of phenomenon we want. If we wanted the convex dual of the spectrohedron, here it's fine to take the convex hull of the dual variety, but you really do need to take the convex hull, unlike for the curve example before. It does not just vanish on the whole boundary of the.
And those don't come from the dual variety.
This is the dual variety, but these not really. I mean, they come from they don't. I mean, they come from it a little bit. They are dual to these 4 points, but this is not. They are not on the dual variety of the.
So Daniel, doesn't this also have these weird sticks that sort of come out that one needs to remove before taking the convex hull? This
contains lines. Yes. I mean, the whole picture is sort of I didn't think this was. You're right. The whole picture is kind of spherically cut off. Right, in mathematics. It's right. So you do actually get.
So 3 separate lines.
Yes, you do get. Exactly. So I should have noticed this before. This is exactly what we're going to see now, also in the matrix examples. Exactly. So there will be some lines.
Remove the
So
lines.
Exactly. So let me show the same phenomenon in the example that I prepared for that purpose. I sort of inserted this at the last minute and didn't think it through. You're quite right.
Daniel,
Yes.
one more thing.
Yes.
So when you put those lids, actually it also has a lot of unexposed extreme points.
Oh yes, that's right.
So it's really a sort of geometrically nasty situation.
Right? Yeah, it's a dual to a spectrohedron. It's not a spectrohedron. It's not have exposed. The geometry is okay. Yeah, this tiny example is endlessly fascinating. It's true. Okay, so So, but without all this nice classical projective geometry, so people looking at the joint numerical range already discovered sort of the same thing happening. Okay, so Chen and Nakazato, who have done a lot of work on the numerical range and joint numerical ranges, so they discovered this example that Kippenhahn's theorem will fail in higher dimensions for much the same reason. So they gave this explicit example of 3 Hermitian matrices where if you, well, this is the determinantal hypersurface that bounds the corresponding spectrohedron. And they computed the dual, and they noticed that the dual variety is singular along a line. And it in particular contains this entire line. And this, of course, will wreak havoc with taking convex hulls. Okay, so here's the picture. So there's this part of the thing which is nice and smooth, and that actually is the dual of the spectrohedron. But then we also get this line. So if you just naively really say, I take the convex hull of the dual variety, no matter how you do this, then this line will destroy the statement that you actually want. Okay, so you have to get rid of the line before taking, you have to remove the line, and then the picture is fine. Okay. So, and yeah, okay. So I just have enough time to get to the punchline. So that's indeed, so the happy ending to this story is that this is the only thing that goes wrong. So this is incomplete generality. It doesn't even rely on spectrohedra. If you start with a hyperbolic hypersurface, and you take the projective dual variety, no matter whether it's a hypersurface again or not, in these examples it was, but as I've showed you, it doesn't have to be. But you take the projective dual variety, and then the convex hull of its real points will still give you the convex dual of the hyperbolicity cone. But you have to first remove all singular points of the dual. Okay, so this kind of thing, whenever you see something like this in real algebraic geometry, when you have a lower dimensional part, where the local dimension is lower, in particular, this means that these will all have to be singular points of this hypersurface, this variety. But no matter what they are like, so you have to, if you remove all singularities from the dual hypersurface, then the convex hull will still be the correct set. It will be dual to the hyperbolicity cone. So in particular, in some sense, this does give a description of the joint numerical range. So if you take the joint numerical range of Hermitian matrices and you take the dual hypersurface to the determinantal hypersurface, its convex hull will give you the joint numerical range. And well, okay, and the proof, I mean, the proof relies on a more careful analysis of what happened, a much more careful analysis of what happened in the plane. But we saw, I mean, at least most of the ingredients already in the plane case. You have to keep track carefully of what it means for a real point on the dual, from what kind of real thing in the primal can it actually come. And then when you take closures, you have to make sure that everything works out correctly. So a careful analysis gives the same thing as for plane groups. And okay, I mean, this is some description of this joint numerical range, and I think in complete generality, there's probably not much. It can't be improved much. What we don't know is whether, for instance, whether there are nice conditions on the matrices that would prevent this kind of counterexample, so where you don't have to worry about the singularities. But I don't know what those conditions could be, even in special cases. So I'll stop here. Thank you very much.
I have 2 questions. Well, in the basic situation, suppose you start with a polynomial in one variable and take its companion matrix. Yes. What about the numerical range? So we have the roots in the plane, and we have the numerical range of the companion matrix. What does it tell us?
It's a non-symmetric case.
Yeah, it's a non-symmetric matrix.
way of studying the roots of a polynomial in one variable.
Arranging the plane. The plane picture.
I mean, the eigenvalues are still the roots. Right? So some of the general statements apply, so it will contain the roots of the polynomial.
But is there anything special about companions? You haven't looked at it? No. And then I have a second question, more general. Could you imagine any kind of generalization to positively hyperbolic varieties?
Josephine, Cynthia?
Do it.
Quick question. So you take the inner product in matrices of trace 1.
Right.
I mean, you could do trace k. I mean, do you get an analogous theorem which can be maybe deduced from this?
Sorry, if you do what? If you do
So
trace?
you look at trace of ak times p, where now p is rank k. Or the same
Yeah,
thing.
so-
Rank K matrices.
Rank K matrices, yes. So I mentioned, exactly. So I mentioned this, so we didn't really look at this, but I mentioned, so there are these people who studied convexity of this thing, right? So, oops, why did I skip past this? Sorry about this. Speeding through the slides. Exactly, Lee and Poon. So they have this, so they did this analysis of convexity of the joint numerical range, and they looked at exactly what you suggested. So what if I don't go from rank 1 to the convex hull all at once, but what if you do it step by step? What can you say? When does it first become convex? They have some general statements, but I mean, at least as far as convexity is concerned, as far as I remember, nothing too surprising happens. So meaning you can have examples where you have to go all the way to square matrices, and you can have examples where it immediately becomes convex, and then you can sort of get many things in between depending on the matrices. But it is a natural thing to look at, yes.
Any more questions?
So let's
Thank you.